Welcome everyone, whichever time of day it is, to this webinar on quantum secure cryptographic algorithm implementations in embedded systems. I'd like to welcome you on behalf of the IET, the three technical networks that are involved, the Media Technical Network, the IoT Technical Network, and the Quantum Computing Technical Network, and in particular to welcome you and to be very pleased to be able to present Karen Villigar, who will be speaking on behalf and works for Kudelski IoT. Her background is as a security specialist and has been working for some while in cryptographic and security architecture for a variety of applications in banking, identity, telecoms, pay TV, and IoT. And she'll be presenting our webinar this evening. Before we get there, though, I'd just like to give a few words to help us along the way. If you have any questions, and I hope there will be lots of good questions, please put those in the question and answer session rather than the chat, and we'll pick those up and collate them and arrange for them at the end of the session after the main presentation. If we could go on to the next slide. So I'm Graham Turner. I'm a member of the IET Media Network Executive Committee, and our interest is very much in media of all kinds. We grew out of being a technical network that was concerned mainly with broadcast, but it's much wider than that now. And if we can go to the next slide, just a little bit about the technical networks. The technical networks are the specialist groups and interests within the IET to enable people to access events either online or in person, and more and more events now are online. There's specialist content that we can provide, opportunities to learn about things, and also to meet and to find out from experts, to learn outside your normal discipline area, and to build continuing professional development towards maintaining your status as professional engineers. And the QR code you'll see on screen at the moment is one that will take you to the main IET technical network page, and then from there you can find out more about the various technical networks involved in this evening's presentation. If we could move, please. So for the media network, we've got some links here. You'll be getting some other links in a follow-up email for the other technical networks, but you can find us on the IET. We have a YouTube channel, and the material from this evening will be going up onto our YouTube channel in due course. And you can find us at LinkedIn at the IET Media Network. If we can move on. So really, why are the media TN interested in this area? Well, we've got an interest because so much media is actually delivered in previously broadcast, but delivered in one way or another to consumers, and media is valuable. It has to be protected. And in the past, the root of the protection, and things like the secure roots of trust within set-top boxes, within display devices, within phones, within really anything which is going to be exchanging data, these tended to use private keys and symmetric keys, but the key management was carried out using public-private key pairs, and these were assumed and have been secure because it's very difficult to factor very large numbers, and very large numbers are used as the keys for these security systems. However, with the advent of quantum computing, suddenly that all changes. There's the potential to actually be able to decrypt content, decrypt material that's protected by the public-private key pairs, and suddenly all of the assumptions about what was secure can be turned on its head. So we have an interest in that because of the impact it has on the fields that we work in, and other people working in this area. If we move on now to IoT, my colleague Rob Taylor will take over.
Good evening, and thank you to Graham from the Media Technical Network for inviting us along to talk about the Internet of Things in the context of the impact of quantum computing on cryptographics and what it means for the Internet of Things. So if we can move on to the next slide, please. Some people regard the Internet of Things as the Internet of Threats, perhaps, but looking at the proliferation, the number of devices out there, it really is the horse is already bolted. But if we look at the types of IoT, we really are compartmentalizing the types of IoT into a risk management strategy. So you're looking at things like the lifestyle products that we possibly wear on our wrists, through to critical medical devices, and energy management. The energy management, when particularly locally to me, involves people putting solar panels and batteries, and are they actually maximizing the use from that? And it's as simple as that. So I don't think the continued growth where it's expected to have in IoT devices, the 2.5 billion per year, as we've seen, will make any difference, but it's all about risk. And we can see we've seen the impacts of AI botnets through the always on, and if you just use Shodan, you can see all those IoT devices which are still on admin passwords and everything else. But what is it we can do? I mentioned risk. How do we risk manage our aspects, every aspect of the IoT's impact on our life? But there are a number of organizations out there, and I always see cybersecurity is do the simple things first. The NCSC provides quite a bit of what I call is bland advice, but nonetheless, it's still giving that overview of what you can do, the simple stuff. It doesn't have to be extremely technical at one level, but it does on the other. The IoT Security Foundation, again, security best practice is another source of information that we can refer to, and that's continually developing. And of course, our NIST colleagues using all the years and years of information they've put together. But it really does, again, boil down to how we manage the risk around the IoT devices, which we use in our everyday lives or in those critical roles, and how that might be managed going on to the future as the proliferation continues. I'd now like to hand you over to my colleague, Darwin Hines. Thank
you. Good day, everybody. Thank you for coming along to the webinar. And I thank Graham and Rob for the introductions. The Quantum Engineering Technical Network was set up to raise awareness of and to provide development and evolution of the quantum engineering profession through the IET. There is a desperate shortage of quantum engineers, and the disciplines it covers are quite broad, all the way through from vacuum devices, refrigerators, precision engineering. I can just go on. So please, if you are interested in a career change, take a look at quantum engineering. And next slide, please. I'm going to do a quick canter through post-quantum cryptography, or quantum safe cryptography, it's also known. 3 decades ago, the threat of quantum computing completely breaking asymmetrical cryptography, specifically public key cryptography, was first realized when Peter Shaw developed his quantum algorithm to factorize large numbers. And of course, public key encryption does tend to rely on numbers that can't be factorized. Also, with symmetrical encryption, Lovegrover developed a quantum algorithm which will speed up the brute force attacks on symmetrical ciphers, thereby rendering them weaker or just reducing their strength. So quantum computers is a complete threat in one direction in terms of asymmetrical, and also it will reduce the strength of symmetrical ciphers. However, you can increase the bit numbers, so it starts increasing the strength again. Now, Michaela Moscow in 2013 developed what's known as his theorem, but a number of eminent presenters do tend to refer to it as quantum's cryptographic apocalypse, saying if the time to keep cryptographic keys safe plus the time to implement a quantum safe solution is greater than the time to develop an industrial strength or scale quantum computer, then we all need to worry. And whilst I won't give you any timescales on the development of an industrial scale quantum computer, it is moving forward very, very quickly. And I think we have 10 or 11 different technologies now providing qubits, which is the base unit of a quantum computer. Realizing this problem, NIST in 8 years ago, asked for a submission of proposed requirements and evolution criteria for post-quantum cryptography. And 8 years later, in August last year, they published their 3 post-quantum cryptography standards, which have been seen to be quantum safe or post-quantum cryptographic solutions. However, the real test is when an industrial scale computer comes along to check it out. The UK National Authority for Cryptography, the National Cyber Security Centre, have published their next steps in preparing for post-quantum cryptography white paper, and I recommend that you take a look at this. There are also some historical white papers covering things like quantum random number generation and quantum key distribution. So I hope you enjoy the presentation. Thank you.
Thank you very much, Derwin. And Karen, now if I can hand over to you, looking forward very much to your presentation. Thank you.
Thank you all for the introduction. I'm sharing my screen. So thank you for the introduction, Graham, Rob, and Derwin. And the subjects that I will address in my presentation follow these threads that has been explained regarding the progress that have been made on quantum computer. And so we will see what is the context and why quantum secure solutions matter now. And we will see how many problems it raised to define quantum secure solution. And in this context, we will have a closer look at side channel and fault attack in context of embedded device and in context of the migration to quantum resistant algorithm. Then we will have a look at what could be practical countermeasures and conclude. So more concretely, if we think about what Derwin just present, we should have in mind that all our digital worlds rely on classical asymmetric cryptography such as RSA and elliptic curve. And so in internet, all secure web browser, email encryption. For banking, we have device and servers that rely on certificate and PKI based on RSA, so they rely on large number factorization problems. For communication, identity, data protection, for other fields. We need what is called security, and for that we have constructed cryptographic algorithms that rely on difficult problems to be able to share what is called a public key and then keep a secret key, a private key, to do the inverse operation. And with the Shor algorithm, all these fields will be affected by the fact that a public key or a ciphertext that is encrypted thanks to RSA, sorry, a plaintext that is encrypted thanks to RSA could be in fact recovered. Indeed, as soon as the factorization will be possible or the discrete logarithm will be solved on quantum computer with enough capabilities, then the private key will not be anymore private, and so all the protection that have been put in place in the digital world will be broken. So it exists several defense. The first one, and there were mentioned some of them. So it relies on quantum cryptography, but this cryptography needs quantum hardware. So the general quantum cryptography will be valid when we would like in the future to communicate between two quantum computers or between quantum hardware. So for the moment, we cannot rely on such kind of cryptography to protect the data. There exists a quantum key distribution, which is already in place for some of applications, but it has some trouble for the authentication part. And so it is not a standalone solution to secure our digital world. You may have also heard about quantum random number generation. In fact, it's the random number generation is key in cryptography to generate the keys, to generate the randoms that we need in protocols. And quantum random number generators are based on quantum mechanics to produce randomness. But it is not with the quantum random number generation that we are able to protect the data. So there is the second axis, which is the quantum resistant cryptography, also called quantum safe cryptography or PQC. And this requires a migration plan, which is in fact today, because the threats related to data that have long life is already there, because we could store now communication and decrypt as soon as a quantum computer with enough capabilities will be available. And if we have a closer look at what are quantum resistant cryptography or PQC, in fact, it's really a cryptography in the traditional sense. And so in terms of asymmetric cryptography, to be able to share a public key and keep a private key, we need hard mathematical problems to construct operation that will be resistant to classical cryptanalysis that could be performed on our current computer, and also quantum-based attacks. That means Shores shall not be able to break them, but also we should keep in mind that new algorithm can be found and can take the advantages of the progress on the classical computer, but also on the quantum ones. And so this algorithm shall be implemented on our current hardware, so in a classical computer, in classical system on chip, or in classical microcontroller. However, what is clear today, it is that the candidates that have been presented through the NIST competition since 2016 are not as efficient as the RSA or elliptic curve-based cryptography were in terms of private key size, public key size, or ciphertext or signatures. And even if there are some progress to make them more efficient in terms of implementation, it is not straightforward. And for each use case, either signature for mutual authentication or signature for firmware authentication, it is clear that it is not the same algorithm that we will use to be efficient. So as Derwen mentioned, there was this competition from NIST, and now we have 4 algorithms that have been selected. 3 are standards, but as we will see in the next slide, we have much more choice available. Even if today we cannot say when a quantum computer will break RSA or elliptic curves, we know that data are at risk for some use case, and so it is important to act now and to understand what we have in the toolbox available. So if we consider some specific use case of firmware authentication or software signature, we have available hash stateful based signature. And this kind of algorithm are relevant for specific use case, but they have some drawback related to the key management side. They have security proofs that are well understood and well mature. So that's one kind of choice we could take for some specific use case. Then in the middle, you have the winner of the competition of NIST. And so we have a key encapsulation mechanism to replace RSA or key agreement based on the discrete logarithms that were used to exchange symmetric keys. And now we have this key encapsulation mechanism based on module learning with error, so lattice, to replace existing scheme or to be used in hybrid mode. In terms of signature, we have a free option. Two have been already standardized in FIPS 204 and FIPS 205. And again, it depends on the use case. For example, FIPS 205 has a very important signature size and will not fit in constraint IoT device as Rob mentioned. In constraint environment, we have a reduced RAM, we have not the possibility to receive a huge payload because of energy or because of memory. And then we have the fourth one, which is based on Falcon, but the standard is not yet there. A draft is announced for this year. On the right side, you can see that there are much more candidates and much more choice in the futures that we will have to consider in terms of implementation and check if they would be efficient or not for constrained device. So if we consider this option, we have also to consider the state's recommendation and the regulations. Since April, we have now a new national security algorithm cipher suite from the US government, which provide a timeline, and it has been updated at the end of last year to give a date around 2030 for the migration instead of several dates that there were before. And we have the standards, as we have already mentioned. But if we consider all the other countries over the world, they have other time frame, they have other recommendation in terms of algorithm, even if some of them converge to FIPS 203, 204, or the SP 208. But there is one thing where they are all aligned is the transition period, which shall start this year because we are in 2025 now, and which should be finalized for 2030. And depending on the countries, RSA and ECC-based cryptography will be considered as disallowed and deprecated after this date. And so why there is this urgency and why states are pushing and why there was so many works done on new algorithm definition, it's because there exist long-term critical assets in government area, but also in medical area, in military area. We have also to consider that products have long life cycles, and we have products that are designed today and that will be in the field for 10, 15, 20 or more in the future. And so at this stage, we could anticipate that quantum computer able to break RSA or elliptic curves will be there. A third point why it is important to consider the migration, it's because from the past, we know that migrating cryptography takes a long time. And the experience to migrate from DES to AES or SHA-1 to SHA-2 was long. So we know that in this context where it is more complex, it will take more time. And an important thing to have in mind for this is that the world has become more and more digital. So we have much more elements to migrate than in the past. We have the government regulations that, depending on the field, of application, for example, for energy or for passport, for identity, will push strongly to have product integrated quantum security. And last point, which is not the smallest one, it's the knowledge to acquire, because as we will see in the next slide, quantum resistant algorithm rely on many things. So to address this needs, and we have to face many problems, and to manage them in a way that it will be the less risky for the use case. We have to manage uncertainty regarding timeline, but it is the timeline related to quantum computer availability, to specification of algorithm, to the maturity of the algorithm. We don't know exactly when we will consider them mature enough. We have some uncertainty because all the country, all the application field do not recommend exactly the same things. Some recommend to follow exactly CNSA 2.0. Some request hybrid cryptography, that is, keep RSA but add MLDSA. We have some uncertainty also on the variants, because in the proposition there are many security level, and depending on the use case, we have to select one or to integrate all. The second problem is the complexity, which is related to the mathematics that are behind this difficult mathematical problems that we should have to be resistant to cryptanalysis and to threats that are brought by quantum computer. We have a complexity in the algorithms, and we will see that in more details. The impact of the new algorithm and the fact that the key size payload will be bigger have an impact on all the protocols that use cryptography. Because in fact, in the digital world, we do not use only algorithm. We have a layer on the top of them to communicate, to construct systems, and that's the protocols. And we all know that the more we have complexity, the more attackers can find attack paths and also a way to reverse secret and get access to things that they should not have. And the third problem is the cost, because we have to update devices that are already deployed in the field and that should stand maybe for 10 more years. We have servers. We have a different solution to handle, because as I have shown before, with the different algorithm, you have seen that you have some algorithm for one use case, other algorithm for other use case, and you still need to handle legacy. The new algorithm requests also more memories in terms of execution, and they may, for some of them, impact the performances and so the energy consumption, which is a problem for IoT area. If we focus now on a specific problem, which is the complexity, in fact, we have today a closer look at the threats on the implementation. We know very well classical asymmetric cryptography, and we know now how to implement them in a secure way, but they will be broken by quantum computer. So we have to handle this quantum resistant cryptography, for which, for some of them, we have some uncertainty related to the robustness, because of the security proof are not completely finalized for some, and we have to handle the side channel and fault attacks. In addition to that, the protocol that will rely on this implementation of this new algorithm will also need a secure implementation and secure countermeasures. To remind you what are the side channel and fault attacks, here I have put an overview. And the statement that we could provide today, with the 25 years of attacks that we have seen in the cryptography area and protocols, is the following one. Whatever the cryptographic algorithm, whatever is security, whatever is robustness in terms of cryptanalysis, the physical execution of its implementation can leak information, enabling to find the secret it is normally in charge of protecting. And so at the bottom of the slide, you could see several kinds of objects that should normally keep secret some elements. And we could use side channel to collect either timing execution, different timing execution, power consumption, electromagnetic emanation during the execution of cryptographic operation on these devices. And thanks to signal processing or well-known attacks such as correlation power analysis or single power analysis, deep learning, we could get the secret. In addition to the side channel attacks, we have the fault attacks. The fault attacks need means for fault injection that are performed during the execution on the component. And this fault alter data, alter the process. And again, thanks to some processing, we are able to get the keys. In addition to these two, we could for sure complement this both attack, so merge fault with side channel and also cryptanalysis to get the secrets. And attackers just have to find one attack path, whereas a designer have to think about all the possible attacks. If we would like to illustrate what I've just said on MLKIM, here I put the sample of the code which is available on PQM free library and which was executed on STM32 platform. On yellow here you have the steps of decapsulation where SK is the secret key. So you want to retrieve the secrets that someone has encrypted with your public key. And you have many operations to perform because on MLKM, we rely on lattice, so we rely on polynomial operation. And we have to handle modular operation between coefficient, which lead to observe many points of interest in the execution and collecting power analysis. We could perform correlation power analysis, and on the right side in the green traces, you see when we made the correct hypothesis on the keys, and with the red traces when we have the wrong hypothesis. And so without any countermeasures, the key could be recovered easily from the low-level operations. So from the past, we have learned how to secure RSA elliptic curves, and I propose that we have a look at what would be the differences. So now, if we consider RSA encryption used to protect, for example, symmetric keys, we had to secure what is called the modular exponentiation. It's the gray box in the middle of the slide regarding side channel and fault attacks. And so for that, we have to secure mainly the modular arithmetic operations that you have on the low level of this slide, which represents the toolbox that we need to implement RSA operation. Now, if we have a look at MLKIM in the same use case where we would like to encrypt a symmetric key, so it is represented here on in the red circle. And then in gray, you can see that we have many more functions to secure against side channel and fault attack. Each time that you have a red value, it's a value that could be attacked by someone thanks to side channel or fault to be able to get information on the secrets that we would like, in fact, to protect with MLKM. And so that gives you a view of the complexity that is different compared to RSA securization or ECC securization. Indeed, we have still to protect the low-level operations, the modular arithmetic, but we have also to protect all the hash function and operation related to matrix, vectors, and polynomial operation with some operations that are sensitive to a side channel. Here, the number theory transformation is the operation that we have attacked just previously, because it relies on modular operations that are sensitive to leakage or fault. So it was to illustrate you the complexity related to these new algorithms. And if we consider all the propositions that have been published in the NIST competition and in the future new signature, we have many difficult problems. We have the lattice one that we have just seen with MLKM. We have hash-based signature that are quite sensitive to fault attack. We have isogeny-based cryptography, which rely also on elliptic curves and on which we could probably replicate all the attacks that we have made in the past on the elliptic curves and found new one because of the complexity. We have code-based cryptography, multivariate cryptography, multi-party computation, and zero-knowledge proof. And for each of them, we have dedicated function to protect and to understand. And that brings me to the steps that will explain how we see the securization. First of all, we should consider the implementation of countermeasures at the level of the algorithm itself. But for that, it is important to understand very well the low-level functions that are used and needed to implement the algorithm, and to identify where the attackers will find point of interest in the execution process. Once we have that, we could consider that the well-known countermeasures such as constant time, masking, blinding, random execution, fake operation, reverse operation as interesting, but they will bring some additional execution time, additional resource usage, and they will need to be adapted for each algorithm to its specificities. But that would be the first step. The second one would be to consider, in fact, the keys, the assets that are handled by the algorithm and the algorithm themselves, and associate to them what we could say life cycle management. By setting in the design mechanism enabling to update for sure countermeasures that we have defined, algorithms themselves, and also manage the key rotation properly in a way that if a keys are at one point with one kind of implementation of the algorithm could have leaked, we could replace the implementation of the algorithm. For example, it is still MLKM, but some new attacks have been found, and so we should update the countermeasures. The key that go through this algorithm should be also updated, because if at one point it has leaked, it is too late. The third axis is to execute the algorithm in a secure environment. That means that if you are executing the algorithm in a device, having physical countermeasure locally is quite interesting to avoid to make the side channel leakage less relevant, to integrate error code detection or error code correction in order to detect fault attacks, adding also control flow. And what we could say also as a secure environment is guarantee that the device that is doing the execution has properly started. That means that the firmware or the software that is under execution is the one that we want, and so is authenticated. The fourth point is, in fact, during the implementation of the post-quantum algorithm, it is important to challenge the implementation and challenge the systems and make the assumption that an attacker knows everything and he knows the design, and so we cannot rely on secret mechanism to be sure that he will not find a weakest path. So it is important to perform in advance some side channel leakage analysis or fault injection on the design in simulation to capture the potential point of interest that we could have missed as the first stage. With that, we should be able to have what we call a secure digital system that will enable to address the quantum threats more simply. So if we summarize, in fact, we should have a strategy with protection. That means that during the development process, integrate security, such as evaluation, but also secure coding rules, secure countermeasures, and perform also in the design architecture solution enabling secure initialization. We should have also some detection mechanism enabling to detect if some things goes wrong. Having also the possibility to react is mandatory. That means that if at one point the execution is able to detect that something is going in a bad direction, it should be able to put itself in a secure state. That means that if you are, for example, in the execution of an algorithm and you have integrated detection and protection mechanism in the implementation, you should be able to see that you are in the next step handling data that if there is some leakage, an attacker will get some information related to the secret. Then you should take another path and do not handle this variable, but handle another one. You should also have mechanism to block the system and, if possible, create a correction in order that an attacker couldn't see that he really performs some things efficient. And the last strategy aspect is to handle, in fact, what we could say quantum secure life cycles, which include updates and also mechanism to put a device in a secure state. So previously it was a secure state for the algorithm, and it could be a secure state until we receive the secure updates, or if not possible, improve the design for a future deployment. So to summarize, what we could say is that securing the implementation of post-quantum algorithm in embedded device against the side channel and fault attack implies some costly operation, because we have to add many mechanisms, the execution time and the memory will be impacted. So it should be done in a detailed approach to not over-engineer the design. And it affects also globally the security of the systems to enable the updates, the key rotation, algorithm rotation if needed. That's the first point. It is essential to adopt a layered approach, combining different mechanisms at hardware level, software level, validation level, in order to be able to adapt the design according to the new threats. And the last point that I would like to share with you is that, in fact, securing post-quantum algorithm implementation is the same thing that securing classical algorithm. It is just more complex because of the complexity of the algorithm, but it shall remain a dynamic process. So thank you for your attention, and if you have any questions, do not hesitate.
Thank you very much indeed, Karen. That was a very interesting presentation indeed. We have some questions. I'd encourage all of those who've been following this to put any more questions you have into the Q&A, and we'll do our best to cover them. Looking at some of the questions, there was one looking at real-world examples of successful attacks on traditional cryptographic implementations, would they have been protected, or how could they have been better protected by quantum-resistant algorithms?
I think if we consider attack on RSA that could have been performed on some existing product in the field, in fact, quantum-resistant algorithm will not avoid them. It will be possible to avoid them if the implementation is robust. But if the attack was due to implementation, the attack will remain, in fact.
Okay, that leads quite nicely into the next. I'll bring a couple of questions together, asking about whether there are any tools and libraries that you'd recommend for embedded engineers looking to experiment with quantum-resistant cryptography, and also about whether there are any standards and frameworks currently guiding the adoption of this in embedded systems.
So for the first point, there are some open source tools available to perform side channel on implementation. So it is possible, thanks to the reference code of this algorithm, to already test this potential leakage that will happen. So there are many tools already available, and some are sold by companies and by laboratories to try side channel attacks. And for the second part of the question, to my knowledge, there is not yet a standards with which integrates side channel and fault countermeasures yet. In fact, what we have seen is that even in the past, AES, for example, is quite prone to side channel and fault attack, and they weren't considered when AES was designed. Now it is these attacks are very well known, but as it is already complex to find a difficult mathematical problem and construct new algorithm, the side channel and fault attacks were not, I think, at the top of the priority, but it is crucial to address them because we could have a very robust algorithm, but if its implementation is not, it doesn't bring any security. But for now, I don't know any standards or ready or even in draft which provide detailed countermeasures to secure the NIST algorithms.
Thank you. I'm looking at some other questions too. There's one about the type or why certain mathematical problems are more resistant to quantum analysis, and also whether there could be any mileage in base options. I guess this would be particularly in the hardware, where there's an assumption that what you're looking at is going to be effectively base 2 when you come down to it, but whether there are other choices that might make it a bit harder to analyze.
That might be, but at one point in the hardware, we are always handling finally bytes or words. And at this stage, even if from high-level perspective, an algorithm seems to be more robust or to have a structure that will be less prone to attacks, at one point we will go in details to really perform the operation. And so, as I have mentioned before, it is important to try to identify the point of interest for each kind of algorithm. But today, in the proposed standards, we have the hash-based one, which are prone to faults. But for side channel, it is less concern because we consider that the key generation and signature generation will be executed in secure hardware in HSM, in hardware secure module, in secure areas, whereas MLDSA, which is based on lattice, and MLKEM In this case, we will have the two operation, even the three operations, the key generation, signature or encapsulation, verification and decapsulation, that could be executed in a device or in a smart card or in a device that will be in the hands of an attackers. And so in this context, side channel and fault should be considered.
Thanks. I've got some more questions now. One particularly set to do with mobile telephony, mobile data, as to whether there are any expectation or plans for quantum-resistant cryptography being built into 5, 6G or retrofitted to 4G and previous protocols.
GSMA, which is the organism which finally group all the telecom fields, has a roadmap and has started to provide a recommendation related to the migration. And companies that provide chip for mobile are also very active in this area. So for the 5G, there are already some prototype, and there were some publication of suppliers that claim to have a hybrid, for example, key exchange. That is, they rely on, for example, differential based on elliptic curves, and they have added a layer with MLKM to secure the exchange of the symmetric keys.
Thanks. Just thinking about a question really about some of the equipment that's already out in the field. Presumably one of the risks is that quantum computers could make what were unviable side channel attacks suddenly viable by sheer brute force.
So, sorry, I didn't get...
With existing equipment out in the field,
Yes.
where there are potential side channel attacks, but which may be unviable because of the amount of data or the amount of possibilities, presumably quantum computers would suddenly make those viable.
That is a possibility, yes. If the device will remain in the field for many years, and if they handle the data that are critical at this stage, yes, because the public key will be available, and thanks to the public key, or thanks to the exchange that could be captured with the quantum computer, it will be possible to retrieve the private key and so break the systems.
Presumably, even if there wasn't a new key being exchanged with existing buried secret keys, the quantum computer might just allow sufficient brute force attacks in a short period of time to break an existing secret key.
So regarding the brute force attack with the Grover algorithms, today it is less critical than executing the Shor algorithms. The resource in the quantum computer that will be needed to execute Grover are much more important than the one requested for Shor. So for now, it is less critical. The symmetric keys algorithm are less in danger, I would say, than the asymmetric key. But maybe there one you would like to add something regarding this?
Erwin, did you want to add something?
Yes, it's not just the old implementations of security on devices, it's also information that has been previously encrypted, either using public key encryption, which means it's susceptible to Shor, or low bit number symmetrical encryption, which means it will be susceptible to Grover's algorithm.
Yes.
But it is potentially brute force is a technique that has been utilized for many years. It is just the strength of the implementation that has fought that off. I really don't know what the implications are for that with the quantum equipment. It's very much wait and see. But I was going to ask a question on these implementations of post-quantum cryptography myself, and that is on the power budget.
Yeah.
Is that going to be a problem for
In fact,
IoT devices?
due to the fact that not all the algorithm, but for example, MLDSA request more memory to be executed, it will consume more energy. That's a fact. And also, given that the data, the signature or the ciphertext are bigger, in terms of data transmission, it brings also an additional cost. Then locally, in the past, we have hardware accelerator to accelerate asymmetric cryptographic algorithm. And if you had a look at the power consumption, when these accelerator are working, then you have a bump in the power consumption. So it will be the same kind of behavior with the accelerator that will help to keep the performances with MLKM and MLDSA or over future algorithm. So regarding the consumption, asymmetric cryptography used to request more energy than symmetric algorithm. But now, in addition to that, we have much more memory to be able to execute them. And we have key size and data which are bigger. So yes, in terms of energy, it will have an impact. And as I have shown for the diagram of MLKEM, you have seen that we have many gray box to secure compared to the modular exponentiation of RSA. So it requests much more operations, so much more energy at the end. In addition, we also have to handle many solutions. So in one design, we will have several algorithms. So it is also more flash to store all the algorithms that before we, for example, have RSA and it was fine. Now we may have hash-based signature LMS. We may have MLKM, but also if you need hybrid, you need to keep ECC-based cryptography. So you need a flash or non-volatile memory with a bigger size. So you need to produce that also.
Thank you, Kari. I don't know, Rob, did you have any questions or anyone else the questions?
My eyes is drawn to the retrofit 5G, well, 2 to 5G. I can't really answer that, but just thinking the cost implications for 2, 3G, if that's phased out as a tech, is probably not worth the investment. I'm not sure if anyone else has got any views on the data network and the introduction of retrofitting crypto technology. Well, quite secure.
For telecommunication,
Really
I think that with the trend that we see for the users, they change mobile regularly, then it will be easier to integrate that than it would have been in the past when we have an old phone, one at home. So I think, yes, there is legacy, but as the end user is used to change his equipment regularly, maybe that's an area where it will be easier. There are areas such as banking where it will be difficult because you have to replace all the reader, all the bank interface. And from the past, it has been difficult to increase RSA key size. So migrating to quantum resistant algorithm will be also difficult. And that's why it is important to do the analyze now, perform cryptographic inventory, perform risk analysis to plan the migration properly, and put the investment in place to be able to do it. But then if you have a product that will be in the field just for 2 years from now, maybe it is not necessary to make a huge investment to secure MLKEM or against side channel and fault attacks. Maybe it is better to secure what you have for the next 2 years. But yes, it is a risk management which is really important to be performed.
Thanks, Harry.
It's interesting, the comment about the 2 years, as we just had a question pop up about how are identity providers, such as passport providers, doing with passports have a 10-year life.
So I didn't have a look recently to the passport standards, but from the past, what I know is that in this field, the key size for RSA and ECC were very, very in advance compared to other field, so large enough to be secure for many years. And so I think the migration plan is already discussed for many years. I think since the NIST launched the competitions, because yes, the passport will stand after 2030 now.
I think you've covered quite a lot about there's some questions about for the ways that alternative architectures might perhaps be used to implement some post-quantum cryptography, and also what are the sort of best practices. But you've touched on the best practice, but really whether there are thoughts about particularly attractive architectures for implementing.
Attractive architecture? I'm not sure.
In terms of the mixture of element types, thinking about what might be going into the way of programmable logic as opposed to pre-programmed devices, even with a very large set of instructions and memory.
You could prepare that, but also you should have mechanism to update. That's key, because you cannot put it is important in security to understand that from architecture point of view, there will be always security weaknesses that will be found. So really the key point in the security architecture is to put in place mechanism to guarantee that at one point we will be able to update the algorithms, the countermeasures, to update the keys, and also to have the possibility to be in a secure state. That means that, for example, today we know that symmetric algorithm, if they have 2056 bits, we will be secure against quantum computer. So you could have in the background mechanisms that will put you from asymmetric to symmetric, for example. That's what you often see as crypto agility, but it is more than crypto agility. It's secure life cycle agility or secure management of the system, in fact.
Thanks. There was one question actually, which I'm happy to answer, someone saying about the sheer cost of this, but I can make the comment that 30 years ago, hackers were willing to spend $1 million to break television systems. So there's no problem, unfortunately, about money for the dark side of this.
And of course, there are services online like AWS, etc., that you can utilize to do your computing.
Yes, and for quantum computing, companies that have qubits provide cloud interface to perform operation on quantum computer. That's the way it is today, and maybe it will remain this way because building quantum computer for the moment is costly. It requests specific environment conditions, but there is this quantum platform that are already there, and you could pay to access them. So we could start to consider the positive aspect of quantum computer, which enable to improve optimization problem for chemistry or finance or machine learning or optimization of the energy management. But yes, we should consider that hackers have access to everything and are ready to pay if they could get much more money after.
You can already do extremely good planning and optimization on a D-Wave annealing machine.
Okay.
You don't need that many qubits.
Exactly.
And of course, Google are doing research on a quantum, so are Microsoft,
IBM.
Amazon, etc., IBM, and they're all providing services online.
Yes.
Yeah.
You have free services, or you could pay for some regular usage.
Thank you very much indeed, Karen. That's been really interesting and thought-provoking. And I'd like to thank you on behalf of all of the people who've joined us, say this evening, but of course they're people from all around the world, so not necessarily evening for everybody. And particularly you're staying later in Switzerland in order to present this. Thank you very much indeed. And I look forward to seeing advances in protecting us against the threats alongside the benefits of quantum computing, the threats that it can deliver to us. But thank you again.
Thank you very much for your attendance and for the questions. Have a good day or good evening.
Thank you.
Thank you.
And if I can just wrap up, Gemma, if we could just move to slide. Just to say that this is one of a number of field notes that the Media Technical Network is providing on security. And the next two that will be coming up are the trust factor one at the end of February. And then beyond that, the anatomy of a hack at the end of March. So if you're interested, and I hope you will be, then please do join us for that. And also, I know Gemma will be sending out information that the quantum engineering and the IoT technical network will be providing, as well as the media one, to see forthcoming events. So thank you very much for your attendance. And once again, thank you, Karen. I really appreciated the joy this evening. And
thank you all.
Thank you.
Thank you. Bye.
Okay, bye-bye.
Bye.
Bye-bye.